Hi everyone, in this lecture we're going to talk about switch mode inverters. Okay. So what are switch mode inverters? So basically we want to convert DC to AC. That's the main thing. So the main objective of inverters is to generate an AC output waveform from a DC power supply. Okay. So if we have our input here as VDC, which is a DC voltage, and then we have a capacitor here, and then we apply that to our inverter plus some filter, right? So at the output terminal, I want to have a sinusoidal voltage or an AC voltage here. Typically what we want is sinusoidal, so I out. So if we were to draw this, for example, this is I and this is V, both of them are AC voltages that are created from a DC voltage here. Okay. So there are basically two types of switch mode inverters. The voltage source input and the voltage source inverter they call, and the current source inverter. So in the voltage source inverter, the input power supply that we explained here is a voltage source, and in the current source inverter, the input power supply is a current source. So in this lecture we're gonna talk about the voltage source inverters because that is the one that has the highest applications, most number of applications. Okay, so let's look at Okay, so let's look at single phase voltage source inverters. Two types of these inverters that we're going to investigate are the half bridge and the full bridge. In this lecture, we're going to explain the half bridge. Okay, so let's look at half bridge. PSI, and basically it's different modulation schemes that we can perform. So first of all, let's look at the topology. So my input has to be a DC voltage, and then I go into my inverter, which is comprised of these two capacitors. Oh, let's just try it. A switch here, and an anti-parallel diode with the switch. Another one here. Okay, and this goes to output. So this is C1, C2, S1, S2, D1, D2, and this is V out. This is the current going out. And let's name these nodes A and node N. Okay, so in here, the voltage of across capacitor C1 and C2 are equal, and they are both equal to half the input voltage VDC. And since the current harmonics injected by the operation of the inverter are low order harmonics, large capacitors C1 and C2 are required. Okay, so what else? So S1 and S2 obviously can't turn on at the same time, because if they do, you will short circuit the input voltage and burn out these switches here. Right, so obviously S1 and S2 can turn on at the same time. S1 and S2 cannot be on simultaneously due to short circuit across the DC link voltage. Okay, or they call this phenomenon the shoot through to the your switches. Okay, so based on okay, so I want to look at my voltage at the output terminal here, right? And this voltage at the output is actually equal to my VA minus VN. So VN, I know, is the midpoint of these capacitors, which is VDC over 2, which is a DC voltage with low ripple. And VA here is determined by whether I am switching S1 or S2, right? So if S1 is on, VA would be connected to the positive end of VDC, and then if S2 is on, and the node A would be connected to the negative terminal of VDC, and this is how we can change V out. So we can have different switching states for half-bridge VSI. Okay, states. This one on, S2 off, S2 off, this one on. So when S1 is on and S2 is off, node A is connected to the positive terminal of VDC, so VAN is equal to V out is equal to VDC over 2. When S2 is, sorry, when S2 is on and S1 is off. When S2 is on, VA is connected to the negative terminal of VDC, so VAN is equal to V out is equal to minus VDC over 2. Now we know that we can't have S1 and S2 on at the same time, but because of that shoot through, but we can have S1 off and S2 off at the same time. So what's going to happen then? So at that time, when S1 and S2 are both off, it's going to rely on the direction of the output current here. If the output current is positive, then it makes this diode D2 to conduct, and therefore the node A would be connected to minus VDC. Right, so VAN is equal to V out is equal to minus VDC over 2 when I out is positive. And then vice versa if Y out is negative, right? So VDC over 2 when I out is negative. So this is for S1 off, S2 off. So we're gonna have these two. So this is an basically unknown state. Now the states for the switches S1 and S2 are defined by the modulation technique. To avoid shoot through and unknown state, the modulation technique should always ensure that either S1 or S2 is on. Okay, so we can have different types of modulation techniques. Right, so the first modulation technique that I'm going to explain is the carrier based. Pulse width modulation technique, or the PWM method. PWM is short for pulse width modulation. Right? Okay, so the PWM enables the output of the inverter, which is V out, is equal to VAN, to follow the desired waveform. Now, this desired waveform in most cases is the sinusoidal voltage and current, right? How does it do that? It does it by defining the on and off states of the switches by comparing a modulation signal VC, or the control signal, which is our desired AC output voltage and a triangle waveform. V delta, which is also called the carrier signal. Okay, so we have a comparator which at the positive terminal I have my VC, which is my control, and at the negative terminal I have V delta, which is a triangle shape waveform. So this is the control signal, and this is the carrier signal. Okay, so VC, which is the control, first let's look at the V carrier actually. So the V carrier is something like this, some kind of a zigzag it goes on. And so important things about the carrier signal is the frequency of the carrier signal establishes switching frequency. So whatever f of delta I have, that equals to my f of s, right? This is the switching frequency. And this is the carrier frequency, they're equal. And another thing is that V delta, we didn't define V delta. V delta is basically the peak magnitude here, V delta. And F delta are generally kept constant. So how do we do our regulations? Basically by changing the control signal. So this control signal determines what kind of output waveform can I expect in the fundamental component of my output voltage, right? So if I have an AC waveform here, AC sinusoidal waveform here, what I expect at the output is this kind of AC sinusoidal waveform. and then so the frequency will be the same as the frequency of VC at the output, but its amplitude will show how we can actually control its amplitude by changing the amplitude of the control signal, but the frequency will remain the same as whatever frequency I have here as my control signal. The frequency of my output, fundamental component of my output signal would be the same. So now where does this go to? This goes to my S1. So when this V control is greater than V delta, or the triangle waveform, S1 turns on. And when V control is less than V delta, this is not, S2 turns on. Okay, so this is how the PWM carrier-based PWM modulation scheme works. Okay, let's bring some waveforms of that I captured before from a book. Okay, so this is from the power electronics converters application and design book. And okay, it shows our carrier signal here, and we have our control signal as the sinusoidal waveform here. So whenever my control signal is greater than the carrier signal, then S1 is on. So whenever this happens, S1 is on and VAN would equal VDC over 2, right? So what we have at this waveform here. So VDC over 2, and we would have this. And when V control is less than V triangle, we would have negative VDC. So this is our output voltage, and as you can see, it pulsates between positive VDC over 2 and then negative VDC over 2. Okay. Now, the important thing is that the fundamental frequency of this output voltage has this sinusoidal waveform, which is basically in sync with whatever our control signal was here. So this is the important part. So after doing some filtering on our output voltage, we can actually extract this voltage or this type of currents out from our inverter. Okay, so now how do we actually have control over the magnitude of this voltage? So we know how to control its frequency, right? So its frequency is the same as the frequency of the carrier. but its magnitude, how do we control that part? Okay, so let's look at, so first of all, when we want to have the our desired waveform, so VC is sinusoidal. It's a special case of PWM, which we call special case PWM, which is called sinusoidal PWM, or pulse width modulation, pulse width modulation, or for short SPWM. Okay, so now let's introduce some concepts. So the first one is the modulation index. Modulation index is MA equals the magnitude of our control signal over the magnitude of our triangle signal, and then frequency modulation ratio is MF equals F delta, which is the frequency of our triangle signal, over FC, which is the frequency of our carrier signal. Magnitude of carrier, peak of triangle. Okay, so from this, VAN, which is our output voltage, the fundamental frequency is equal to MA sine of omega 1t times VDC over 2, where omega 1, so this is VAN that we showed here, this pulsating between VDC and minus VDC over 2, and this is actually its first harmonic or first component. So first component of VAN is this, it's a sinusoidal voltage, and its amplitude is MA times VDC over 2, and its frequency is equal to the same frequency as what we had as our carrier signal, 2 pi FC. Okay. So now it's important to note that MA here is only valid when it is less than or equal to 1, and so for this case, VAN 1 varies linearly with MA. Thus, this is called the linear region. One important thing to note is that the maximum value in the linear region that we can achieve for the first component of VA and its magnitude is when MA is equal to 1. So the maximum value that we can achieve is VDC over 2. And we can't have an AC output where its magnitude and the fundamental component of it, the magnitude of its fundamental component is greater than VDC over 2. Now, if you want to do that, we have to go into overmodulation, and that has its own drawbacks. Okay, now if we look at the output voltage again, so we saw that it's either positive VDC or VDC over 2 or negative VDC over 2, as you can see here, right? So now we know it has a fundamental component, but it has some other harmonics as well, right? Okay, so it's fun. So in this graph here, you see it's the harmonics. It's harmonics. So it has a first order harmonic, which is the sinusoidal voltage here, and then it has some harmonics at its switching frequency. So and its sidebands, right? So the inverter output voltage appears at sidebands, which are basically centered around its switching frequency, which is, for example, MF. So remember here, because this is the harmonic side, so it would be MF multiplied by FC, which would be FS. So this is really FS, and then this is 2FS, and it's sidebands plus 1 plus 2. So this is how the harmonics basically show itself. Okay, so for if mf is larger than 9, is sufficiently high, the harmonic amplitudes are almost independent of mf. So the amplitudes you see here, if mf is large enough, so these amplitudes won't be affected by the actual value of mf, and it's mainly determined by your value of ma. Okay, so now let's look at what harmonics, at what frequencies these harmonics occur. So we said it's harmonics and its sidebands, right? We can say that the frequency at which voltage harmonics occur is f of h equals j mf plus k multiplied by fc, right? So this is the number, the harmonic number, and it's multiplied by its fc to give us the frequency at which voltage harmonics occur. Right? So if j was odd integer or just an odd number, then k has to be even. What does this mean? So if you look here, here we have 1 mf, so 1 is an odd integer, an odd number for j, right? So k has to be even, so 1 mf plus 0, I have a value. 1 mf plus 2, I have a value. 1 mf minus 2, I have a value here. That's what it means. Right, so you can see the same thing for 3 mf. So 3 is an odd number, so I have a value at 3 mf plus 0, 3 mf plus 2, 3 mf plus 4, and you get the idea. But the magnitudes decrease as we go along the side bands. So what happens if j was even? If j was even, k would be odd numbers. So 2 mf as I have here, 2 mf plus 0, I don't have anything here. But 2 mf plus 1 and minus 1, I have a magnitude. So plus 1 and minus 1, as you can see here. So this is what it means. So this is how you can find the frequencies at which voltage harmonics occur. Okay, and another interesting thing is that, so if mf is chosen as an odd integer, Okay, so if I have an odd integer as mf, so here if this was odd I would have, so let's say if I had mf equals to 7, and then at harmonic 7 I would have a value, and I would have a value, another value, magnitude as 7 plus 2 which is 9, and then 7 minus 2 which is 5, and here I would have a value 2mf plus 1 which is 15, and then 4 okay, and then here I would have a value for 2mf which is 2 times 7 plus 1 which is 15 and 13. So I would have harmonics at odd, basically only odd harmonics, and at even harmonics I don't have a value, any value. Because of that, the output results in an odd symmetry where ft is equal to minus f minus t, and half wave symmetry, which is basically ft is equal to minus ft minus ts over 2, where ts is the switching time period. Let's just write it as fs because we've defined fs before. Okay, with synchronous PWM. Synchronous because we have integer. Okay, so this is for the linear region, but what if we wanted to achieve a voltage at the output? So I want the first component of my voltage to be higher than VDC over 2. So I have to go into overmodulation where my MA exceeds 1. And so let me bring another picture here. Okay, as you can see, if my MA goes above 1, I go into overmodulation. And in overmodulation, my MA does not have a linear relationship with the output voltage anymore. Although I can achieve a higher voltage, but it won't be, basically it won't have a linear relationship. And so yeah, so that's the advantage of MA greater than 1 Advantages: higher magnitude of VDC over 2 can be achieved, and its main disadvantage is that it has many more harmonics than what we saw in the linear, so that's the main disadvantage. Many more harmonics as subbands. Okay, so now you see that if we have a large enough MF, so a large enough MA, this goes into basically a square wave. For sufficiently large value of MA, the inverter voltage converges into square wave. So now let's look at the square wave. So this is basically another modulation technique, which is a square wave modulation technique that we can use, but from what we explained right before, we now know that it's just a particular, just one specific condition in a pulse width modulation technique that creates our square wave modulation technique. So the good thing about this technique is that it's very simple, and that is, so if this is VAN, then I would have VAN on as VDC over 2 for half of the cycle, and equal to minus VDC over 2 for another half of the cycle. What I mean by cycle is basically the carrier cycle, 1 over FC, not the switching. Well, here it's the same. So VAN it's a square wave, right? So VAN, the fundamental component 1, is equal to 4 pi divided by VDC over 2, which is equal to 1.273 VDC over 2. And its other harmonics, VANH magnitude, is equal to VAN1 divided by N. Okay, so I forgot to mention here that this photo also is from the Power Electronics Converter Application and Design. by Mohan. And okay, so let's get back to this, the square wave modulation technique. What is its advantage? So the advantage is that each switch basically only changes its state only twice per cycle. So each switch changes its state only twice per cycle. So as you can see, so for example here and here is twice, but in the SPWM or the PWM, if you remember, so we had this sawtooth, so this this would change like this. So we had a lot of switching happening at each cycle. So what's the main disadvantage? The main disadvantage, if you look at here, is that we don't have MA anymore, and that means that we can't adjust our output voltage by the switching pattern. And the only way to control the output, the magnitude of the output here, is really to just change the input voltage. That's the main big disadvantage there. Okay, so this advantage is that output voltage cannot be regulated, thus VDC must be adjusted to basically control the magnitude of the inverter output voltage. Okay, so this is it for the half bridge inverter. In the next lecture, we're going to explain the full bridge.